Alright, in this video what we have here is an example for calculating a one-way ANOVA by hand. Now you would use a one-way ANOVA in a situation where you have three or more groups and it's a between subjects or independent groups design. Now for the hypothetical experiment that we're working with, we have individuals, specifically 5 per condition, who were given a driving test where they had no phone, had to talk on a handheld phone, or had to talk on a hands-free phone. Then what we have here for actual data is their scores on that driving test from 0 to 6, let's say. And what we have is higher scores correspond to a higher score on the driving test. So this would be a situation where you would use a one-way ANOVA. Now, just like other statistical tests, you still go through the same process where you state your hypotheses, set your criteria for rejection, calculate your test statistic, interpret your test statistic, and then finally report your results. So we're going to go ahead right here and get going in stating our hypotheses. Now, the null hypothesis for an ANOVA essentially states that there's no difference between these groups. In other words, sample 1, which comes from population 1, has a mean that's equal to population 2, or the population that sample 2 came from, and so on and so forth for the third population as well. Now, writing the alternative hypothesis is a little bit tricky, because really what ANOVA tests is if one of these different means is different. It could be that these two are not equal, these two are not equal, or none of them are equal to each other. An ANOVA won't tell us which one. So when you think about the alternative hypothesis, it's actually just the negation of the null. So if you were to sort of write this out with logical symbols, you would write a little tilde or whatever signal you have for not, and you would write out all that again. Now what this means is essentially that everything inside the parentheses is not true. So any one mean could be different and negate that. Another way to state this in words, which is perfectly acceptable, at least one pair of means is different. Either is acceptable. You don't have to list out every single possibility of things that are not equal to each other. Now, after we've stated our hypotheses, the next thing we need to do is we need to set our criteria for rejection. All right. Now, we are going to conduct an F-test to run this ANOVA. If you hear F-test and ANOVA, they're very, very similar things, and ANOVA is a type of F-test. An F-test looks things up based on the F distribution. The F distribution is positively skewed and bounded at 0, such that we will always have one critical value that's in the right-hand tail, and only a single critical region. Now, in this respect, if I can remember how to spell region. Now, this runs essentially the same way as all the others do. If the test statistic we calculate falls in this critical region, then we reject our null hypothesis and accept our alternative hypothesis. What we need to do is find out what this critical value actually is. Now, to do this, you actually need to look it up based on both of your different degrees of freedom. Now we'll get into this in a little bit more, but an ANOVA has a degrees of freedom for the numerator or the between subjects variance, and a degrees of freedom for the denominator, or the within subjects variance. When we look at the degrees of freedom between, that is going to be the number of conditions we have minus 1. Now in this case we have 1, 2, 3 conditions, so that would be 3 minus 1 to get us 2. Now when we look at the degrees of freedom within groups, what we're actually looking at, this is between groups and within groups, not subjects. What we're looking at here is the total number of scores in the entire experiment, capital N, minus the number of groups that we have. We have 5 here, 5 here, 5 here. 3 times 5 is 15, so we have 15 total participants minus 3 conditions to get us 12. So based on these two numbers, we would then go look up a critical value. Now, most statistical tables are set up something where you have to look up both the degrees of freedom in the numerator base for the column and the degrees of freedom for the denominator. I'm not even going to try and spell that right now. And then you would have this table. Now, if we did this, our degrees of freedom in the numerator would be our df between, which would be 2, and then 12. Now, in this case, that value is going to be equal to 3.88. So if we get an observed test statistic greater than 3.88, it'll fall in this critical region, and that's when we'll actually reject our null hypothesis. Now, we're going to go ahead and go to the next sheet in terms of calculating our test statistic, but I'm going to kind of throw it down onto the side so we can still see our data, so to speak. Now, when we're going to calculate our test statistic, it's helpful to keep everything in a table. Now, this is a specific type of table called an ANOVA table, and it's where we'll put the output from all of our different formulas in it. So, first column of this table is going to be the source, or source of variance, the sum of squares for that source of variance, the degrees of freedom for that source of variance, the mean square for that source of variance, and then our final F value that we end up calculating. Now, in terms of rows, we're going to have a row for the between groups variance. For the between groups variance, the within groups variance, and then the total variance. Now, we will go through and calculate all these one by one. We've actually done the degrees of freedom here as well already when we looked up our critical value. But we will get to that in due time. So, treat each individual cell in this table as a separate subgoal and work towards them all individually. So the sum of squares between is going to be equal to the sum of the treatment total squared divided by the size in that treatment condition minus the grand mean squared divided by the total number of scores in the entire experiment. So there are 2 or 3 new symbols, depending on how you look at it, that we need to pay attention to. T, which is the sum of scores inside a single condition. So inside the no phone condition, if we were to add up all these scores, we would actually get 20. This basic math has already been done for us in this example. N, specifically lowercase n, is the number of scores in that group or condition. 1, 2, 3, 4, 5. G stands for the grand total, which is the sum of all the scores. Now, this number, the grand total, is actually 30, but you could add up all of those and double check me if you want. So when we go to actually solve this, what we really need is the treatment total squared for each condition. So 20 squared divided by the number of scores, which is 5. There are 5 in each group, plus 5 squared divided by 5 plus 5 squared divided by 5. And then we need to subtract out that grand mean, or grand total, 30 squared, and then we need to divide by the total number of scores. We have 3 conditions, 5 people in each condition. That gets us 15 total scores. Now it's just a simple matter of running out this math. So 20 squared gets us 400 divided by 5 plus 25 divided by 5 plus 25 divided by 5 minus 30 squared ends up being 900 divided by 15. Now, you could, at this point, either convert all of these into decimals, or seeing as they all have the same denominator, just add them across. I'm just going to add them across and keep everything as a fraction. So 400 plus 25 plus 25 gets me 450 divided by 5 minus 900 divided by 15. So now is the point where I'm actually going to need my calculator a little bit, because I can't do 450 divided by 5 in my head anymore. This gets us 90. 900 divided by 15 gets us 60 minus 60, and this gets us an overall sum of squares between of 30. Once I have that number, put it up in the table right away. Now let's hit our next sub-goal, the next thing we need to work for, the sum of squares within. Now the sum of squares within is just adding up all the sum of squares from each treatment. That's what SSK means. Now those sum of squares have already been calculated for you. If you're not given them, you would have to look back at how to calculate the sum of squares and do that. But fortunately, we don't have to. We just have to add 6 plus 6 plus 4. 6 plus 6 gets us 12, plus 4 gets us 16. Now, to check your math, do the sum of squares total. You don't actually need it to calculate the test statistic, but in this case, you should do it to check your math. So SS total is just the sum of squares for the entire experiment. So it would be sigma x squared minus sigma x, which is also the grand total, so G squared, divided by the total number of scores that we're working with. Now, you could square each of these values and then add them all up, or you can be like me and do it before you ever recorded the video. And so sigma x squared here is 106. And then we're going to subtract out from that our grand total, 30 squared, and then we're going to divide that by the total number of scores we have, 15. Now, you may be tempted to say, hey, I already did this math up here. Do it again. You're trying to check your math. If you made the error right here previously, you're just going to repeat that error here and you won't detect it. So do it all again from scratch. So 106 minus 30 squared, 900 divided by 15. 106 minus 900 divided by 15 gets us 60. 106 minus 60 gets us 46. Now, here's where you can check your math, because another way to calculate SS total is to take the sum of squares between and add them to the sum of squares within. So when we add 30 plus 16, we should get 46, which we do. All right, so that checks out. Now, the next thing we need to calculate is our degrees of freedom. Now, we've already done that previously, but I'm going to do it again here just for the sake of, giving us the practice. So the degrees of freedom between is going to be the number of conditions that we have minus 1. We have 3 conditions minus 1 to get us 2. The degrees of freedom within is going to be the number of scores that we have minus k. So 15 minus 3 to get us 12. Now, what we didn't do previously was calculate the degrees of freedom total. And it is similar in that the degrees of freedom between and within should equal, or the sum of them should equal, the total degrees of freedom. So when we take SS between and add it to SS within, it should equal that degrees of freedom total. Another way to calculate it so we can check our math is to take the number of scores that we have in the entire experiment minus 1 to get us 14. 2 plus 12 will be 14 as well. So we are all good in terms of our math. The next things we need to calculate are the mean squares between and within. We do not do it for the total, just for between and within. We already checked our basic math, and we did all that calculation here. So let's go with the mean squares between. Now, you don't actually really need to write out the formula here, because what it actually is the sum of squares between divided by the degrees of freedom between. So you're just dividing across the row here. But it would be 30 divided by 2 to get us 15. Again, we could divide across the rows here, but I'm going to go ahead and write out the formula for the sake of the video. So for MS within, it's going to be 16 divided by 12, which we get from SS within, divided by our DF within. Oh, if I can spell within today. Yeek. All right, so 16 divided by 12 gets us 1 1/3, or 1.33 repeating. Now we're actually coming to that F value, that test statistic we've been working towards. Now, the F statistic is also called the F ratio because it is the variance or mean square due to between groups factors divided by the within groups variance. Now recognize that the DF within ultimately goes into the MS between, which is why the DF between, when we looked up our critical value once upon a time, was the DF between for the numerator and then conversely for within, it's the denominator. So again, we're really just dividing these two numbers right here. So MS between is 15, MS within is 1.33. Repeating, and let's see what this gets us. 11.25. All right, so we have our final test statistic calculated out. Now what we then have to do is interpret this test statistic. Now, the best way to interpret this is to actually come back to the sketch we made initially. Now, if this is 0, and here is 3.88, where does our calculated value actually fall? Is it over here between 0 and 3.88? No. It would actually probably be way out here in the critical region, but we'll just sketch it in right here as FOBS. 11.25. That is tiny to see, so I'm actually going to redraw that. If we were to sketch it all out again, here's our FDist. It's bounded by 0 over here, and then it's positively skewed. We have a critical value that we looked up previously of 3.88. And then we have that observed test statistic, which is not between 0 and 3.88, but it's actually 11.25, which is out here. So our test statistic is falling within the critical region. Therefore, we end up rejecting the null hypothesis, because this critical region are those F values that would be unlikely to happen due to random chance, specifically less than a 5% chance, because we're using an alpha of 0.05. Now, we've interpreted this test. We know at least one of these means is significantly different because we've rejected this and we're accepting this. Now, the limitation of an ANOVA is that we do not know which mean pair is actually different, which is why you have to do post-hoc testing, which will actually come in the next video. But before we get there, let's go over how you would actually end up reporting this ANOVA in the text. So, if we were going to go about reporting this, we might say something like a one-way ANOVA was used and it found at least one of the means was significantly different. Now is when we actually go about reporting our ANOVA, specifically the statistics from it. Now, an ANOVA is a type of F-test, so we use the capital and italicized letter F to indicate that. Then, just like a t-test, we report our degrees of freedom, but now we have two different degrees of freedom. Now, you always report the numerator first, or the between groups degrees of freedom, which, if we look back to our ANOVA table, we can see was 2. Then we add a comma to separate the DF between from the DF within. Then we let people know that the F statistic we actually calculated was 11.25. And then we add a comma. Then we need to make a statement about the probability of getting this test statistic. We either need to give an exact probability, or we can give it in reference to whatever our alpha level was. In this case, 0.05. Thinking the wrong thing. We need to write a P, and in this case, seeing as we are less than our alpha levels indicated by our test statistic falling in the critical region, P is less than 0.05. So that's how you would actually report an ANOVA on the test or in a paper. You will see in older papers where they actually give you the full ANOVA table. This is not typically done and has fallen out of current practice, but you could still do it if you wanted to, I suppose. Nevertheless, this is the standard APA style reporting of a one-way ANOVA. Now, in the next video, we'll build on this and we'll write up our different post hoc tests. But that'll come in the next video when we actually go over how to calculate those post hoc tests.